Recorded rolling. It is Wednesday, March 4th. Right, so a few things here before we get back to your FRQ packet, and then we'll continue from there. All right, we have course selections coming up. Now, I got an email, so I'm going to throw the email text up here, so we're all looking at the same thing. Here. All right, zoom in here. All right, it says, as we get the process for course selection for this next coming school year, okay, change your procedures. There's just something a little bit different than in the past. Yeah. In the interest of streamlining process and improving student communication, we'll be asking students. Okay, here we go. Here's what's important to you guys. Asking students to submit their elective selections. Boink, right there. Directly into focus. Directly into focus. Have you guys seen a message, something like that? Wait, did I hear somebody say yes?
I've heard.
Okay, that might be coming up in the next couple weeks, maybe. Right? They will be they will select their core courses on the traditional course selection sheet. Oh, okay. So that looks like actually the part that I highlighted with focus looks like elective specifically.
Yeah, I like that.
Right? And then something about core courses on a traditional course sheet here. Right? In the past, teachers provided recommendations for selection sheets. This year, we'll be soliciting your input after the students have made their selections. So it's going to be students first, and then I guess teachers can go back. We evaluate. Okay. Blah, 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 blah. Right. I think that's Right. I think that's the main thing that you guys need to know from that. Okay. So if you look, I don't know when they're going to put that out or have you guys decide. But it's probably the next couple weeks. Okay. Right, so be looking for that. Now, also speaking of course selection, like, what do you have to graduate? Okay. So I know between science and your social science classes, I'll say maybe social studies. Right. What I've heard over the last few years, so unless this has changed, it's probably still the case. Guys, how many total classes do you have to graduate? 7. 7 total. Okay. So it can be, guys, it can be 4 science and 3 social studies, or 3 and 4. Okay. Okay, since you're sitting in physics right now, you almost certainly had biology and chemistry right now, right? Okay. So physics, right? So this class would be 3, right? And then okay, so that's there. All right, so you guys go with 4 seconds so far. Okay. Right, next thing I want to hit is this question here. So going back a couple of quizzes ago, you guys remember that simple harmonic motion quiz? Right, there's one question near the end that said if you have a block on a spring and you pull the block back, some amplitude A, let it go and oscillates. Okay. Guys, what part of this process, where would the block have maximum speed? Through what point? Yeah, right through the equilibrium point. Okay. And through the equilibrium, of course, how much does the spring stretch? Not at all horizontally. Okay. Even if you turn this vertically, you say, well, wait, but the spring be stretch. It's still mathematically works out the same. Okay. Okay. Ask you guys, what does the graph of Vmax versus amplitude look like? Okay. Some of you guys got this, some of you guys did. But I was looking at the quiz corrections you guys were doing, and it looked like I don't know how many students were able to explain why this graph looks like this. So I'm going to tell you guys why this would be a linear relationship. Like if you pull this back 3 times as far, it's going to end up going 3 times the maximum speed. Like, why would that be? Okay. All right, so I can show this with conservation of energy real fast. So sum of energy initial equals sum of energy final. Okay. Now, the initial condition might be like the picture right here, where you're pulling the block back some amplitude A. Guys, when you do that, you're holding the block to rest. Guys, look here. Guys, think about this. Guys. I don't know how many of you guys know why this graph is linear. Okay, so, but I'll show you. It's about the process of thinking. Right? So you pull back some amplitude A. Guys, what type of energy does it have? What? Yeah, spring potential. Isn't that like 1/2 kx squared? 1/2 kx squared. But instead of x, I'm going to say A for amplitude. Right? That's a common thing to do. Okay. And that's all the energy. Now, guys, everybody taking notes? When it's going through the equilibrium, hence it would have max speed, which is the other part you're interested in. What does the energy term look like right there? Yeah, kinetic, which is 1/2 mv squared. Okay. Even more specifically, V max. Okay. Because that's the only type of energy when it's going through the equilibrium. So, okay. And you got to figure out what's the relationship between this here and this here. Guess that? Okay. Now, what's constant is the spring constant. Okay, because spring's not changing. Also, the block's not changing. Okay, so that's all constant. So if all the stuff is constant, the one half obviously cancel. Can you guys say the amplitude squared is proportional to Vmax squared? Right, that'll be true, right? Right. Are you allowed to take the square root of both sides? Right. If you do that, you get the amplitude is proportional to Vmax. Okay. Actually, if you wanted to get this as an exact equation, it would be okay. You'd be dividing over the k and then taking the square root, so it'd be root m over k times Vmax. Okay. So that would be an exact equation. So I think the slope of this line would be the square root of m over k. I mean, I wouldn't be totally surprised if that shows up on the AP exam, something like that. Okay. So you guys get that question? Okay. Great. All right. What are you guys gonna have done by the end of the weekend? Yeah, AP Classroom Dynamics 1. They might have to go digging for this assignment because open this way back up in August. Back in August. So remember, the first 19 questions are multiple choice. That's the ones I really want you to answer. Number 20 is an FRQ. Don't worry about doing anything for that to turn in. But I do want you guys to read that, and I'll probably go over it in class early next week. All right. Actually, one more little thing. Did you guys hear recently? What was up in the sky a couple days back? Blood moon. Right. So the moon was turning red. Now I missed the time on this because it said the date was yesterday. I was looking for it last night, but it was actually like in the early morning, not last night. So oops. Right. But right, guys, why does the moon turn red? Yeah. Because the sun hits the atmosphere. Exactly. Yeah. Victor knows. Guys, what color is the sunset? It's like red. Right, so here's the sunset. Here's a whole line of sunsets. If you back up and look at it right from space. Right. Yeah, so here comes sunlight. Right. Yeah, so yeah, all of our sunrises and sunsets are simultaneously refracted on the moon. Yeah, we'll fit it there. They have approximately once a year. So yeah, next time you see the opportunity for that, it might be a window of just a couple of hours. Maybe that would be okay. Right. Yeah, if you ever see the moon turn red, you're seeing all our sunrise comes up at the same time. We hit this detail. Guys, tomorrow SAT. I think most of you guys are taking SAT tomorrow. Yeah. So I guess I'll plan around that. Alright, so back to this packet then. We are on number 3. Now, number 3, we started reading yesterday, and then you guys were thinking about it last night. Remember, this is the experimental design question. Now, I looked ahead a little bit in the scoring guide, and actually, their write-up is actually really brief, a lot shorter than I thought it was going to be. So maybe this will be a test of conciseness. Okay, can you strip this down to fundamentally what they're looking for here? All right, but here, read this. Brian, guys, what's going on? Guys, focus here. You're about to be writing some stuff. I think you guys have a blank back size of paper that you guys can write something. We got a platform with unknown rotational inertia, I not, that can rotate with negligible friction about an axle. So that's a nice simplification. There's no friction, no axle friction. A known torque can be exerted on the platform. A known torque. The students are asked to use a graph to determine the rotational inertia. The students have a rotational motion sensor. Okay. Now, pause right there, because when we got to this point, and I showed you guys this yesterday, so I'll remind you guys again today. Right? We basically did this lab, but with different measuring equipment. Right? You guys remember this with the PC pipes? Right? This whole thing? Right, set? Yeah. All right, so yeah, we were measuring, we were changing out this mass, this weight. We were saying it's going to fall some distance. We were measuring this time. Right? And we're putting this together to figure out, ultimately leading towards what is this rotational inertia. Now, we got it from a graph. We got it actually from that graph right there. Okay. But here you have different measuring equipment. You have a rotational motion sensor. Okay. And what does that measure? Well, that can measure 3 things. Angular position, how far something turns. Angular speed, how fast is something rotating. And angular acceleration, maybe the rate that it's speeding up. Spinning. Of the platform as functions of time. The students do not have any way to directly measure I naught. The platform cannot be removed from its axle. So basically, you can't use an alternate method of using a rotational inertia table. You have to put this in motion and have it spin with the torque and everything. Okay. All right. Part A. Indicate quantities that could be measured by students that would allow them to determine the rotational inertia using a linear graph, and double I briefly described a method to reduce experimental uncertainty for measured quantities. Again, I glanced ahead of the scoring guide, and their answer was actually very, very concise. It was just a few sentences. Okay? So here I'm going to pause this video, and you guys go ahead and write down what you think would be a qualifying answer. Here, you know what? Here, guys. Here, I got recording resume, but let's go down to part B because these kind of tie together. So I'll have you guys also do part B before I show you the scoring guide. Okay? It says indicate what quantities students could graph on horizontal and vertical axes to create a linear graph to determine I naught. Okay? And briefly describe the relationship between I naught and a feature of the graph from part B. Okay? Which is usually here. I'll give you guys three options. It's either the y-intercept, the slope, or the area under the curve. Depending on how you set it up. Okay? Your answer may include an equation that relates I naught and a chosen feature from the graph. Again, these part A and part B really go together. Okay? So whatever procedure you chose for part A directly leads to what kind of graph you would create and how you would interpret that graph. Okay. So I'll give you guys another minute here. I'm gonna pause this video again. All right, and we're back recording. Okay, so let's go over to scoring guide. All right, so part A, what's the procedure? We got 2 points here. I told you guys their answer was very, very precise. Right, so here's their model answer. But first, what are the details they're looking for? Okay. Right, so 1 point earned for indicating that the angular speed or angular acceleration should be measured. Right, because there's a couple different ways they went about doing this. Right, couple ways. I would have gone with angular acceleration myself, but there's a way to get it from angular speed also. And 1 point for including a way to reduce experimental uncertainty, either repeating each measurement several times, that's specifically if you went with the angular acceleration, or performing the experiments with different amounts of time, like letting it go on longer and longer and longer. You guys, if you let it go on longer and longer and longer, wouldn't the angular acceleration be the same? But what about the angular speed? That would be increasing with time, wouldn't it? Right. So really, different amounts of time pairs with the angular speed version. Okay. Okay. So these pair together, and these pair together. Okay. Great. So here's your example response. Exert the known torque on the disk. Okay. Measure the angular speed of the platform multiple times while the torque is exerted. I would elaborate on that a little bit. I'd say that maybe every 5 seconds or something like that. Okay. Or the version I would have done is exert the known torque on the disk. Measure the angular acceleration. I would have said angular acceleration instead of angular speed. Then I would have said just repeat that several times over and over. Now although there is only one angular acceleration, so on the graph it would show up as a single point, but you can make sense of that, and I'll show you guys how soon. Okay. All right. So you guys good with that? Okay. So again, very, very concise. Like the whole procedure was just a couple sentences. Okay. All right. So populate yours too. All right. Then part B. What are you gonna do with this? How are you gonna make this a graph? So 2 points here. 1 point for describing a graph that would have a slope. That's the feature of the graph, regardless of which version of this you did. Okay. The slope that is related to rotational inertia of the platform. Acceptable responses may include. Okay, so they give you a good couple of examples. Right? So torque is a function of alpha. Again, that's the one I would have done myself, although that would have been a graph with basically a single point, or maybe 2 points if you include the origin. I'll show you guys what it looks like here in a minute. Right. Or omega is a function of time. Now that you could get a series of points. Although the slope would not exactly be the rotational inertia, but we'll go through how you get it from that. Okay? And then the next point for a description of how to use the slope to calculate rotational inertia of the platform. So we got if tau versus alpha's graph, torque versus angular acceleration, the slope of the graph is the rotational inertia. Right? So that one's like real straightforward, which is of course exactly the last step that we did in our version, right? Tau versus alpha, the slope was the rotational inertia. Okay? Now, if you graph omega versus time, the slope, it says is equal to the torque divided by the rotational inertia of the platform. Okay? So you have to do like an extra step to find the rotational inertia, but it is in there. You're able to find it. Okay? So let's look at this here. I got a couple of sets of axes right up here. So it said you could either do torque versus angular acceleration, or you could do omega as a function of time. Okay? And each of these would work at how. Okay? So here, give you guys a little visual because it might be kind of similar to this. Because once you have, if you only have a known torque, do you guys notice that they kind of imply there's only one torque? Right. Versus when we did in class, we used lots of lab weights. We had like 5 different torques going on. Right. But we just got one torque here. Oh. Now if there's no torque, if there's 0 torque, what's the angular acceleration? 0. So you do get this point kind of for free, don't you? Like 0, 0. Right. Also, they said there's no friction. That kind of goes hand in with that too. Because when we did it in class, there was some frictional torque. So actually, we had a point up here. But there's, and then if there's one torque, it's going to be just one angular acceleration. Now, guys, you could do multiple trials, but you're going to get the same angular acceleration over there. So for one known torque, you might get something like this, like a point here and a point here and a point here. Right? So you might get like a few points that are all kind of bunched together. But you can also connect it to this point. It can make this graph zip. Okay. And then, since you guys know that net torque is I times alpha, but the net torque is the applied torque because there's no friction, then what's the slope of this graph equal to? Rotational inertia. Okay, because it goes torque equals rotational inertia times angular acceleration. Tau equals I alpha. It's kind of F equals ma, but rotational. Right? Yeah, right?
We went there too. That's why I was like,
yeah. Now, if you do omega versus t, guys, what would this graph look like? Could you let this go for like 5 seconds, 10 seconds, 15, 20, 25? It could be time in seconds. Okay. And then, do you think the omega would be increasing also at a linear rate? So you get this point, this point, this point. Okay. So it would look like this, wouldn't it? But then the question is, how do you dig the rotational inertia out of that? Okay. Guys, what do you know for well, right. I think there's a few ways to go through it. Right? Actually, you could start with this, couldn't you? You could start with this. Right. So there's no friction about the axle, so that's nice. Right. So we got this torque resulting in I times alpha. Right. And guys, where's alpha on this? Where's alpha? What's the slope of this line? Yeah, guys, the slope is alpha, isn't it? Okay. So does that go back to, well, I don't have my rotational kinematic ready to go, but ready to go linear kinematic. Isn't it kind of like this right here? If this was omega finals, omega initial, this is alpha t, right? That's that graph, isn't it? This is omega equals, well, I'm going to say alpha t because it starts from rest. Right? Okay. Right. So you could get alpha out of this. And then you say, well, if I know alpha and I know the torque, right, which tau equals I alpha, you could do this. You say tau equals I alpha, where this is the slope of the graph. Okay. So if you want I, could you just take the known torque and divide by the slope of the graph?
Logan's is like,
and that would be the answer. Okay. Right, you guys see that? Which is exactly what they said. But what you guys see that an equation for. Okay. Say it one more time. It says for this one right here. It says the slope is equal to net torque divided by rotational inertia of the platform. Actually, they wrote it this way. They said alpha equals tau over I. That's the direct translation of that sentence. But you can rearrange it and get like that, couldn't you? Okay. It's also the same thing. All right, so you guys good there? All right, so a couple points. All right, you guys ready to move on to next part? Next part. All right, information applies to part C and D. All right, so guys, part C and D, they completely change the scenario. So we're starting over. Oh, so it's gonna be also. Okay, well you guys will see. It's a related question, but it's an entirely new experiment. In a similar experiment, students are given a platform of unknown rotational inertia. There is negligible friction about the axle. So another nice simplification. The students have lumps of clay of varying masses. Ooh, and we got a table down here. Let's look at this table. Ooh, do you guys think that this capital M column represents the mass of the clay balls? I think so. In each trial, they measure the initial rotational speed of the platform, then drop a piece of clay at the very edge of the platform. The students record the final angular speed of the platform. Okay, that looks like these two columns right here. The following data shows the initial final rotating speeds and the mass of the clay. Right? Does this make sense that if it's rotating at say 4 radians per second, and then you drop the clay on it, what's it going to do? Speed up or slow down? Yeah, slow down because there's more inertia. Right? Okay. So maybe conservation of angular momentum sort of thing, or maybe I'm giving away too much. Okay. students correctly derive the following equation, which represents the experimental data collected. Right? So they come up with this. Now, sometimes AP will do this. I would really like you guys to be able to derive this from scratch. So they're making this claim. Omega initial over omega final equals mr squared over the rotational inertia of the platform and then plus one. They're claiming that. Right. Sometimes like if they wanted you to derive that, it's like, well, this FRP is getting too long and blah 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 blah. Right. But I think it's good to be able to do that. Right. So let's go through this. See if you guys can figure this out. Right, so we got this situation right here. Right, so this is rotating. Hey, isn't this a quiz question? You guys had this a quiz question, didn't you? Right. Well, this one's new. I just made this a few days ago. Right. So it was rotating its own initial angular velocity. We're going to drop this ball of clay. It's going to stick right here. Its own distance v, or maybe you can call that r. They go with r. They probably went with r. Whatever. Right. There's some initial rotational inertia of the disk itself. Right. And then. Guys, what's the guiding principle here? What's the very first line? Yeah, conservation of angular momentum. And what is angular momentum? Is what times what? Yeah, I times omega. Right? Guys, isn't that analogous to P equals mv? Right? And throw up on your pages too. Yeah. All right. It's right. It's right here. It's about halfway down your AP equations. Okay, so you got that too. All right. Oh, did I do? Or okay, it's giving away much here. Okay. So initially it's I omega, but after you drop the clay on, isn't it I plus md squared, and then omega final? Right? And omega final is going to be, of course, slower than omega initial. Slow it down. Okay. So you can do something like solve for omega final. Okay. Now it looks like to go for. Are you guys good with this process so far? Right, you guys got that in your notes? And of course, you had to do this for a recent quiz question anyway, a few weeks ago. Right, so let's see if we can take this right here and manipulate it so it looks like this. That would be good to be able to do. Right? So they did the ratio of the angular velocities, initial divided by final. Guys, if I do initial divided by final, can I just divide this omega final over? Okay. And then can I take this I, cross divide it, and I plus md squared and cross multiply that? Can I do that? Okay. Let's do that. Okay. So we're working towards this. But we have this omega final equals I omega initial divided by I plus. I'm going to change this to mr squared. Instead of d, I'll do r. Wherever the clay lands, we'll call that point r from the center. Okay. Now we got to see if we can possibly manipulate this to look like this. So I'm going to divide down the omega final. So I'll have omega initial over omega final, like that. Okay. Then so divide this down here. Then I'm going to take this I, divide down there. I'm going to take this whole thing in parentheses and cross multiply it up here. So it's going to be I plus mr squared all divided by I. Okay? Right, okay? Okay. Now guys, could you split this up into different fractions? Okay. So omega initial over omega final equals I over I plus mr squared over I. Isn't that true? Ah! Is that exactly what they told you? Is look at this. This is this. And I over I is 1. Okay, so you guys see where this is coming from? Okay. Yeah, so something you definitely should be able to do. Okay. All right, so everybody's getting that in their notes. All right, give you guys time to get that in your notes. You guys got that? All right, everybody's got that. Got that. Okay. All right. So now we have an understanding of where this comes from. So omega initial, omega final represent the angular velocity. Okay. Before and after a 6 platform. M is the amount of clay dropped. Okay. And R. Oh, they have a fixed R. They're calling the radius 0.4 meters, so 40 centimeters. It's like almost half a meter stick. Is the distance from the center of the platform to the point where the clay strikes the platform. So what I was calling D here, they're calling R. The students create a graph of within the mass of the clay plotted on the horizontal axis. I mean, that makes sense, right? Because the mass of the clay is sort of like the independent variable, right? We're changing the mass of the clay, right? So now what?
So we know
Label the vertical axis of figure 1 with a measured or calculated quantity. Include units as appropriate. We're talking about like kilograms, radians, seconds. What's going on here? The graph quantity should yield a linear graph that can be used to determine the rotational inertia of the platform. Okay, you see that? Right. On the grid provided here, create a graph of the quantities. Clearly label the vertical axis with a numerical scale. Because you need a variable here, also units, and also put some numbers. Plot the corresponding data points on the grid. Table 2 is provided in your booklet for scratch work and will not be scored. Okay. Draw the line of best fit. Okay, line of best fit. Okay. You're starting with this data right here. And somehow you have to create a linear graph, and your x-axis is this mass of clay at the end here. All right, so I'm going to pause this recording, give you guys a few minutes to think about that. Here, create that graph. All right, here, guys, I just restarted the recording. Just real brief. I want to show you guys a hint. There's something weird about this graph. Guys, what do you notice about?
It starts.
Yeah, you guys see it starts at 1. Oh, that's like fingernails on the chalkboard to me. Okay, but you guys do notice, but there's probably a reason they did that. Do you guys see why they would start the graph at 1? You guys see that? Okay. Okay. So, but okay. So just be aware of that. All right. So pause recording. All right, and we're back. All right. So playing off this, recognizing that this graph starts at 1, so we're probably using this right here. Guys, if this has a y-intercept that they're heavily defined right here, what do you think goes on the y-axis? What do you think they're trying to put the y-axis? This ratio right here, do you guys think? Right? Guys, I think this is y equals mx plus b. Okay. And what's your x value? Is mass? Okay. Guys, I think this goes like this. Y equals, here's your slope. M, here's your x-axis value, x plus b. Isn't that y equals mx plus b right there? You see that? Okay. I think that's what they're heading towards. So what I did is I found all these ratios right here. And I went back to the original table. Right? A lot of times people actually give you extra blank columns to help guide your thinking. Like, oh, you might have to do some calculation. Right? I wish they had done that here. So omega initial over omega final. I just took the ratio of these all the way down. And I came up with all these numbers. You see that? Okay. Then I took these coordinates. So I'm going to graph here. I'll show you guys my graph. Okay. Obviously, mass is on the horizontal axis because they gave that to you. Okay. On the vertical axis, I chose the ratio of the angular velocities. Okay. Now, remember, their graph starts at 1. So this would actually be down the origin on the grid paper that you guys have, but that really bothered me, so I didn't do that. But I plot all the points, and yeah, guys, it looks like all the points do line up in a straight line, and it does go through 1. Right? So that's the graph right there. Right? Now, just walking around, it looks like some of you guys came up with that exactly, which is awesome. Some guys had some other ideas that did not linearize like that, right? Okay, so that's exactly what they were looking for. Right. Right. Here. So, I know there's a lot, so yeah, go over that one more time. Okay. So they gave you this, and then of course we drive behind the scenes where they got that from. It's like, okay, we checked it out. That makes sense. I see where that comes from. That's nice. Right? And then we said, hey, this is going to be the form y equals mx plus b. Okay. On the axes they gave you, they gave you the x value as the mass. Right? They gave you that y-intercept at 1. Right? They're heavily implying there. Okay? And you had to recognize that the y value would be the ratio of the angular velocities, right? Which would be unitless, wouldn't it? Omega over omega, wouldn't that be a unitless value? Right? If you plot all the points, and yeah, it sure does line up in a straight line. Of course, I had to go find the ratios, blah, 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 like that. Okay, you guys get that? Right. And of course, where this is going is the next question, which is calculate the experimental value of the rotational inertia of the platform. With the rotational inertia of the platform. All right, so let's find the slope. Okay. And guys, I marked out right here exactly what the slope represents. Isn't it r squared over I? R squared over I? So here, I'm going to do this with you guys because we got just enough time. Okay. So let's find the slope right here. So I'll tell you the slope of the line, which is rise over run. Okay. Okay, here, let's go do a shortcut because we got like 2 minutes. So I'm gonna go, here, I'm just gonna take this point right here. Let's do, the rise would be 1.48 minus 1, because this is 0, 1, divided by the x, change at 0.76. So 1.48 minus 1, that's kilograms, over 0.76 kilograms. This is unitless. Okay, so I'm getting 0.63, and that's 1 over kilograms. 0.63. Okay. Now that's the slope of the line. That's not the final answer yet. But we can use that because now that you know the slope, you guys can find the slope of the line, right? Okay. Now we can set that equal to this, and we can get the rotational inertia. So let's go to that. So I know r squared over I, which takes the place of the slope in my formula,
There we go.
is equal to 0.63. And that's 1 over a kilogram. Okay. We're solving for I. Oh, do you guys remember radius was 0.4 meters? You guys remember that? Okay. So 0.4 squared is like 0.16. Right, and that would be meter squared. Okay, over I equals 0.63, 1 over a kilogram. Okay. So I equals, right, cross multiply that, divide that, 0.16 over 0.63. We got meter squared up here, the kilograms flips up on top. Yeah, guys, kilogram meter squared. Doesn't that describe I? Okay, let's see what is this. 0.16 over that is, I'm getting 0.25 kilogram meter squared. Okay, that's what I'm getting. Okay. Now, let me see. Okay, this is the last question, the last part of this question. Let's see what the answer key says. Okay, so what did they get? Okay. All right, so last couple points here. 1 point for correctly relating the slope of the line to the rotational inertia of the platform. Again, it was a little bit of a procedure here, but there was a way to do that. Okay. 1 point for calculating the correct value. And they said if they gave a window of answers, so you've got anywhere between 0.19 and 0.28 kilogram meter squared. Wait, so what we got? Oh yeah, that's in there. That's in there. 0.25. Right, so this window of value is right here. Okay. All right. Right, so guys, hang on to these packets. I'm probably not going to see most of you guys tomorrow, but yeah, we'll do number 4 next time we get a chance.